Here is a question. Take every even number and divide it by its nearest odd neighbors. 2 divided by 1 times 2 divided by 3, 4 divided by 3 times 4 divided by 5, 6 divided by 5 times 6 divided by 7. Keep going. Multiply all of these fractions together forever. What do you get? Every single term is rational. Every single term is a simple fraction with small numbers. There is no geometry anywhere in this expression. No circles, no curves, no angles. Just integers and multiplication. And yet, the answer is pi over 2. This is the Wallis product. It was discovered by John Wallis in 1655, decades before calculus was formalized, and it is one of the most beautiful identities in mathematics, an infinite product of mundane fractions, converging to a number that encodes the circumference of every circle ever drawn. Let me write it out. P over 2 equals 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7, and so on forever. You can also write it compactly as a product. The product from n equals 1 to infinity of 4n squared divided by 4n squared minus 1. Look at the partial products. Multiply the first two fractions. You get 4/3, about 1.33. Multiply the first 4. You get 64 over 45, about 1.42. Keep going. The product climbs, slowly, towards pi over 2. It converges, but it converges painfully slowly. After 100 terms, you still only have 2 correct decimal places of pi. After 1,000,000 terms, you have about 6. This is not an efficient way to compute pi. That is not the point. The point is that it works at all. The point is that an infinite product of rationals, none of which involve pi, none of which involve circles, somehow assembles itself into the ratio of a circle's circumference to its diameter. Where does the pi come from? Think about that for a moment. You write down 2 over 1, 2 over 3, 4 over 3, 4 over 5. Nothing but small integers. You multiply them together, over, and the result creeps towards a number that no finite decimal can capture. A number that is irrational, transcendental, and fundamentally tied to curved geometry. And there is not a single curve in sight. Let me show you why. The standard modern proof uses an integral that Johann Wallis himself could not have known, but it is clean and beautiful, and reveals exactly where the circle hides. Define the integral I sub n as the integral from 0 to pi over 2 of sine to the n of x dx. This is the integral of sine raised to the nth power over a quarter of the unit circle. Already you can see the geometry starting to appear. The limits of integration go from 0 to pi over 2, 1/4 turn, 1 right angle. The circle is baked into the domain. Now I sub n satisfies a beautiful recursion. You can prove, using integration by parts, that I sub n equals n-1 over n times I sub n-2. This is the reduction formula. It links each integral to the 1-2 steps behind it, and it lets you unwind the entire sequence, like pulling on a thread that unravels the whole fabric. Start at the bottom. I sub 0, the integral of sine to the 0, which is just 1, from 0 to pi over 2. That equals pi over 2, and I sub 1, the integral of sine itself, equals 1. Now use the reduction formula to climb. I sub 2 equals 1/2 times I sub 0, that is 1/2 times pi over 2. I sub 3 equals 2/3 times I sub 1, that is 2/3. I sub 4 equals 3/4 times I sub 2, that is 3 over 4 times 1/2 times pi over 2. I sub 5 equals 4/5 times I sub 3, that is 4 over 5 times 2/3. Do you see the pattern? The even integrals all contain a factor of pi over 2. The odd integrals are all purely rational, and both sequences are products of simple fractions built from consecutive integers. Let me write them out explicitly. I sub 2n equals the product of the odd numbers from 1 to 2n-1, divided by the product of the even numbers from 2 to 2n, all times pi over 2. And I sub 2n plus 1 equals the product of the even numbers from 2 to 2n, divided by the product of the odd numbers from 1 to 2n plus 1. Now here is the key observation. As n grows, I sub 2n and I sub 2n plus 1 become very close to each other. In fact, their ratio approaches 1. Why? Because sin of x is between 0 and 1 on the interval from 0 to pi over 2. So sin to the 2n of x is slightly larger than sin to the 2n plus 1 of x everywhere on that interval. The integrals are squeezed together, and their ratio converges to 1 as n goes to infinity. This is the squeeze. The even integrals, which carry the pi, and the odd integrals, which are purely rational, are being pressed together until they become equal. Take the ratio I sub 2n divided by I sub 2n plus 1. This ratio equals the product of all those odd over even and even over odd fractions times pi over 2, and because this ratio converges to 1, we can set it equal to 1 and solve for pi over 2. When you expand the ratio and simplify, what remains is exactly the Wallis product. 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7, and so on, equals pi over 2. That is where the pi comes from. It was hiding inside the integral of sine, which lives on the unit circle, which encodes pi in its very domain. The fractions in the Wallis product are not random, they are the coefficients of the reduction formula, laid out in sequence. They are the skeleton of the sine function, expressed as ratios. Let me show you a second perspective, because the Wallis product connects to something even deeper. Consider the sine function, not just on 0 to pi over 2, but everywhere. Sine of x has zeros at every integer multiple of pi. 0, pi, negative pi, 2 pi, negative 2 pi, and so on. And Euler discovered that you can write sine of x as an infinite product over its zeros, just like you can factor a polynomial by its roots. This is the Euler product for sine. Each factor in the product vanishes at x equals n pi, giving sine its periodic zeros. Now evaluate this at x equals pi over 2. Sine of pi over 2 equals 1. So 1 equals pi over 2 times the product of 1 minus 1 over 4n squared. Rearrange, pi over 2 equals 1 divided by the product of 1 minus 1 over 4n squared, and 1 minus 1 over 4n squared equals 4n squared minus 1 over 4n squared. So pi over 2 equals the product from n equals 1 to infinity of 4n squared over 4n squared minus 1. Factor the denominator, 4n squared minus 1 equals 2n minus 1 times 2n plus 1. So pi over 2 equals the product of 4n squared over the quantity 2n minus 1 times 2n plus 1, which is 2n over 2n minus 1, times 2n over 2n plus 1. Write out the first few terms. 2 over 1 times 2 over 3, 4 over 3 times 4 over 5, 6 over 5 times 6 over 7. That is the Wallis product, derived from the infinite product representation of the sine function. Two completely different proofs. One uses the reduction formula for powers of sine, the other uses Euler's product formula. Both arrive at the same identity, and both reveal the same underlying truth. The Wallis product is really a statement about the sine function, and the sine function is really a statement about the circle. Every time you write down 2 over 1 times 2 over 3, you are secretly encoding information about where sine crosses 0. The fractions are not arbitrary. They are the DNA of a periodic function. Let me put the convergence in perspective. The partial products of the Wallis formula approach pi over 2, but they do so agonizingly slowly. After 10 terms, the product is about 1.53. The true value is about 1.57. After 100 terms, you are at 1.566. After 1,000, 1.5703. Each new pair of fractions nudges the product a little closer. The even numerators pull it up. The odd denominators pull it down. The tug-of-war settles, in the limit, on pi over 2. But the rate of convergence tells its own story. The error after n terms is proportional to 1 over the square root of n. To get one more digit of accuracy, you need roughly 100 times more terms. This is not a practical algorithm, it is a theoretical marvel. And it was discovered in 1655 by John Wallis, who had none of the tools we use today. No integration by parts, no Euler product, no formal definition of convergence. He arrived at it through a sequence of interpolations and guesses, comparing areas under curves with known formulas for combinations. It was an act of mathematical intuition that took 3 centuries to fully justify. 370 years later, the Wallis product endures, not because it is useful for computing pi. We have far better algorithms for that. It endures because it tells us something profound about the structure of mathematics itself. Consider what we have actually shown. Take the simplest objects in mathematics, the integers, arrange them into fractions, multiply them together, and out comes a transcendental number that governs every circle, every wave, every oscillation in the physical universe, not approximately, exactly. In the limit, the product of those mundane fractions equals pi over 2. With infinite precision, the integers contain the circle. The circle was there all along, hiding in plain sight, waiting for someone to write the right fractions in the right order.